Do you have any questions, ladies?
No.
No. All right, so let's start the class then. I'm starting to record. Okay. I'm going to share my screen. What we are going to do today, we are going to see various examples from optimization theory in economics. So today I'm just going to describe those problems, and that'll be basically the end for this section. Maybe I should tell you where we are in the syllabus. Let me show you. Okay, this is the Moodle page, and as you can see, well, we have covered already the first topic. And what we are doing today is covering the second topic, which is optimization in Rn. So we gave some theory. The last time we started with some examples, and today will be the last lecture for this topic. So we're going to continue with more examples. So that's the idea of the class. And the examples that I'm going to mention are all going to be just described. So we're not going to solve them. I'm going to provide a description of those problems. Okay, so let's continue then with some examples. And these are optimization problems. Okay, and precisely in economics. Okay, so we provided two examples before, so this would be example number 3. And it's called profit maximization. And I'm going to describe next what this problem is all about. As I said before, so we are just going to try to describe these examples, and that's it. We're not going to solve them. We're going to provide them in general. In this first example, you can suppose that we have some company. And this company produces a single output. Or you can imagine some product. But to do that, they need to use various inputs. So they require a finite number of inputs. So let's say n inputs. Okay, just for notation, so we're going to label those inputs. So inputs are labeled from I equal 1 to n. And we are going to use the variable xi to represent the quantity of input I. Okay, so far so good. So we have this company and they produce some product, and to produce it they require other stuff, other inputs. So we suppose that xi is the quantity of input number I, and y is actually the quantity, the amount of output. Okay, we're going to consider a function of production. So this function is a function that's going from r plus n into r. So, and we're going to call it the production function. Which is sometimes also called a technology function. And how does this work? So the amount of output is going to be given actually by g of x1, x2, so xn. So that's what this represents. So this is going to be the number of, let's say, items or the quantity of the output in terms of the amounts x1, x2, so on. We can represent this also as g of x, where x is x1, x2, so xn. All right, more notation. So we're going to suppose that there is a price for each of the input items. So Wi is going to be the unit price for input I. And as you can expect, Wi is greater than or equal to 0. Okay. And the next feature is probably the most interesting one of this model. So we're going to consider a function p that goes from r plus into r plus. P is going to be a function in terms of y. So in other words, the quantity of the output. And P is called technically the demand curve. Now, what is this going to represent? So this is going to represent the price of the output. So unit price, I mean. In terms of the offer. Offer. Okay, this is all the notation. Whenever you're ready to change the page, please let me know.
I'm ready.
You ready? Thank you. Okay, so there is something that we can note. Well, first of all, I forgot to mention, maybe I should mention again. So R plus is the non-negative real numbers. Okay, and also R plus N is R plus times R plus times so on R plus. And this is N times, right? I think we had mentioned this before, right?
Yes.
Yes, thank you. Okay, so very well. So something that I'd like to notice is that the production price well, this is going to be W times X, right? So W is the vector of prices for each of the inputs, and X is the vector of inputs. Now we understand this as inner product, right? Which means that this is the sum of the Wi times the Xi. Okay, so those are all the assumptions and the notation. Now the goal is to find an input choice such that the profit is maximized. So more concretely, the problem is a maximization problem. So we're going to maximize profit. Okay. And this is going to be a difference, right? So it's going to be the difference of the product, the income minus the outcome. Maybe the outcome is easier. So you see, these are the costs. So this is the production cost. So this is W minus X. Okay, so that's the amount of money that we have to invest to produce the outcome. And now the gain, the income, So you see the function y, I'm sorry, g. The function g, the production function, tells us how many outcomes y we produce. So if we produce g of x, and remember the price for each of these is going to be given by this function, then the income is this multiplication. So number of outcomes produced times the price, the unit price. And of course, we have some restriction in this case. The restriction is that x is in r plus n. Okay. So this is a profit maximization problem. Okay. Do you have any questions, ladies?
No.
No. Okay. So remember, so in this case, we're just describing these problems. I'm going to describe the next one, the next problem, which is problem number 4. And this problem is called cost minimization. Okay. So this problem is similar to the problem that we talked about, one of the problems that we talked about yesterday. So as you see, this is going to be a minimization problem, which I'm going to try to describe next for you. There are various assumptions. So what we would like to do is we want to propose a mix of inputs that minimizes the cost of production. Okay, so we want to propose, as I said before, a mix of inputs that minimize the cost of producing at least certain amount of units of output. Let's say at least y bar units of output. You can notice immediately that this last condition is a constraint. So the production amount should be at least y bar. Okay, again, we're going to have n inputs. With the amounts are going to be given as before. And in this case, again, G is going to be the production function. And again, it's going to be a function that goes from R plus N into R. Okay. Okay. Can we change the page?
Yes.
Yes, thank you. Okay, this production function, by the way, again, it's called a technology function, but I'm not going to mention it again. More notation, so W is going to be the vector W1, W2, Wn. And again, this is going to represent the vector of input prices. Okay. And once again, we suppose that W is in R plus N. About the restriction can be put in a what we called in the previous semester a feasible region. I'm sorry, region. And I'm going to represent it in this way. So this will be f of y bar. It's going to depend on the this number y bar, the least amount of units produced. It's going to be the collection of x in R plus N such that the production is greater than or equal to y bar. Okay. Again, remember, G represents the production function, okay? Now, in this case, the problem is the following. So as we said, we would like to minimize the cost of production. So in other words, we want to minimize W times X subject to the condition that X is in this feasible region. Okay. So again, this is the cost function. Okay, which is again, here it's the inner product. So let me go back for a second. The cost function is going to be given in these terms, right? So this is going to be the sum. Now, something that I would like to point out here is that the feasible region depends on y. I'm sorry, y bar. And in other words, so this depends on one parameter, on the parameter y bar. And thus, this is an example of parameter dependent optimization. This is an example. Okay. Okay, any questions?
No.
No? Okay, very good. So these are two examples. Sometimes we are going to provide some problems in which we are going to consider particular forms of, let's say, in this example of the function g, and we are going to try to determine if there is a solution, and if there is a solution, we are going to try to obtain it. Okay. Meanwhile, I'm going to provide another example. So this is example number 5. And this example is called consumption leisure optimization. Okay. This example falls into a category of study in economics. So it's actually related to a topic called labor supply and decision processes. Especially in households. But it's also related to the utility maximization problem that we talked about in the last class. Okay, so let's try to describe this problem. Well, in this problem, we are going to suppose that there is an individual, which we are going to call agent. So there is an agent. And he has a certain amount of time to spend. So the agent okay, and this amount of time is we're going to represent it by h. And of course, this is greater than or equal to 0. Okay. Can we change the page?
Yes.
Yes, okay, thank you. So remember, this person has a certain amount of time to spend, which is age, and this person can use it doing some activity or doing nothing. So next page. Now okay, so the agent can choose to do something or do nothing. Okay, so he can choose to use the time productively or not productively. But when he works, when he uses productively this time, he has some wage. Mhm. Okay, and we are going to represent this by W, and this is greater than 0, so that's going to represent the wage rate, and that's for productive time. So notice that if the agent works for, let's say, for L units of time, obviously L is going to be greater than or equal to 0 and less than or equal to H. Then he earns some income, and this income is equal to W times L. Well, as an easy consequence, you observe that 0 is less than or equal to W times L. This is less than or equal to W times H. Okay, as I said before, this agent can have some leisure time. So, and we're going to assume that for leisure time, this agent has also may have some profit. All right. In this case, there will be a utility function. It's going to be a function that's going to go from R plus m plus 1 into R. And I'm going to describe this function. So this function is going to depend on x1, x2, so on, xn, and also L. L is the leisure time, which, as you can see, that's h minus L. During the times that this person works, we're going to suppose that has to purchase some commodities in order to obtain some profit. So we suppose that xi is, let's say, the consumption of some commodity, so the amount. Of commodity I, so for I equal 1 to n. And we are going to suppose that these commodities also have some price. Okay, and that's going to be represented by this vector. So P is going to be P1, so on, Pn. In R plus n, so this is the vector of commodity prices. Okay, so let's talk about the feasible region. Okay, I don't have space, so I'm gonna wait for you to copy.
We are ready.
You're ready? Okay, thank you. About the feasible region, this feasible region is going to depend on two parameters, so P and W. And it's going to be the collection of these points in R plus n plus 1 with the property that this cost is less than or equal to the amount this person earns. And L is less than or equal to H. And it makes sense, right? Because leisure time cannot be greater than H. And the person cannot spend more than he receives. Okay, so that's the feasible region. And now the problem. The problem is simply to maximize the utility, which is a function of both x and L. And the condition is that XL is in the feasible region. Okay, so this is the consumption leisure choice problem. And as you can see, once more, this is a parameter dependent optimization problem. Okay. Any questions so far?
No.
No. Okay. All right. So I'm going to describe another problem. So this would be number 6, I think. And this problem is called portfolio choice. Okay. So in this case, you have an agent. So there is an agent. And this person has some choices, certain amount of choices. Okay, and in this case, well, S is a natural number, right? Okay, one of these choices is going to be called the true state or current state. All right. We're going to have also a utility function. Which I'm going to represent by capital U. Okay, so it's going to be again a real function. And the domain is R plus S. So again, so remember, R plus S in this case is R plus, cross R plus, cross R plus, and this is a number S of times. Okay, so we assume that there is an income for each of the states. That's my next assumption. So for each of the states, so the states are S equal to 1, so on, up to S. The income is represented by Y subindex S. Um, and of course, this is a lowercase s, right? Okay, so more precisely, the utility function is going to be a function of these incomes, so of y1, so on, y capital S. Okay, can we change the page?
Yes.
Okay, thank you. Okay, another assumption is that, let's say if the true state is just say S, okay, and remember, S can be any number between 1 and capital S. Then in this case, the agent has an endowment which is going to be represented by WS. And this is a number in R plus. Okay, in other words, this is like the agent's initial income in state S. Okay, so okay, and we can put all of these numbers in a vector. So for the sake of convenience, I'm going to call this vector W. So W is going to be W1, comma, so on, WS, capital S, which is what we call the initial endowment vector. All right. Another assumption is that the agent can change their income when we change it from one state to another. So let's mention that. So the agent may change income from one state to the other. And he can do that by selling what we're going to call securities. Okay, so we are going to assume that there is a finite number of securities. So there are n securities. And we are going to suppose that these securities also have prices. Okay, so let's mention that. So for each of these securities, so we're going to represent the security by I, where I can be 1, 2, so on, n. 1 unit of security costs certain value. So we're going to represent this by pi, and we suppose that pi is greater than or equal to 0. So this is a cost, but we're going to suppose that it also provides some income. And this income is going to be represented by z subindex is. So that's in the case that choi s occurs. Okay, more notation. So any vector of the form phi1, phi2, phi(n), this is obviously in Rn. So any vector is going to be called a portfolio. Okay, and given a portfolio fee, then we're going to define the income in state S through the next formula, but maybe I should wait for you to finish copying. Please let me know when you finish. Oh, you're ready? Okay, thank you. Okay, so the income in state S will be given by the sum from I equal 1 to n of the ith component of the portfolio times ZIS. Okay, so we're adding over all the securities. We are multiplying phi I, the portfolio, the option, times the amount of money that pays for the security, given that the choice S happens. And this is for the state S. So we can also define the overall income. Okay. So this is going to be a function of phi. Then it's going to be given by WS plus the sum from I equal 1 to N. Okay, basically these terms, so that's phi I times ZIS. Okay. Okay, so no, okay, in the case that y of phi, you know, y of phi is going to be y1 of phi, comma, so on, ys of phi, ys I said. So if you consider this vector, then the utility for portfolio fee is actually given by the utility function evaluated at y of phi. Okay, so okay, so we're going to say that fee is affordable if certain condition happens more precisely. So we say that the portfolio fee is affordable if, let's say, the amount made from the sales of securities is sufficient to cover the purchases. Okay, and this condition will be translated into the following: P times, I'm sorry, yeah, P times phi is less than or equal to 0. Is less than or equal to 0, greater than or equal to 0? Yeah, greater than or equal to 0. No, less than or equal to 0. So we're also going to impose something that we're going to call the consumption policy. which states that ys of phi must be greater than or equal to 0 for every s from 1 to capital S. Okay, with all of this notation, the feasible region is the following. Okay, it's going to be a set that's going to depend on the security costs. So it's going to be dependent on the vector P and W. It'll be the collection of all portfolios such that these two conditions are satisfied. This one and this other one.
We wanted to ask what interesting notation you're using before P and W. What is the letter before that?
Oh, do you mean this one?
Yes.
Okay, that's my capital fee.
Ah, okay, we thought so. Okay.
You thought so? Okay, good. So you see, phi is a very rich letter, or phi. That's what they call it in America now. So lowercase phi is this one, but also this one. No, these are. Oh, I'm sorry, lower cases. But then the uppercase, I mean, it should be like this, but bigger one. So this is the way I represent the capital one.
Okay.
I'm sorry. So, but yeah, it's interesting. It's interesting notation. So, but it's after all capital phi. Okay, so that'll be the collection of all portfolios that satisfy these two properties. So satisfy this first one, and that this vector okay, I'm going to write down ys of phi greater or equal to 0 for all s from 1 to capital S. And the problem, finally, is going to be again a parameter dependent problem. So you want to maximize utility. So this is in terms of portfolios. When portfolio is in this feasible region. Oops. All right. Okay. Can we change the page?
Yes.
Yes. Okay. So again, so this is an example of a parameter dependent optimization problem. And there are some particular cases of interest. One of them is the following. It's in the case when the utility function has the form sum for I equal 1 to s of I times some function u of yi. In this case, well, you see, this is a linear combination of independent functions. And these factors can be seen as weights. In fact, Ri is going to be the probability that state I occurs. And as you can imagine, the sum of all the probabilities must be equal to 1, right? Okay. Okay, very well. So this is another example. I still have time to mention one more example. And this is called Pareto optima. Okay, let's talk about this problem. First of all, I'd like to mention that in this case, there is more than one agent. Okay, and we are going to consider now the case of two agents. I mean, for a better description. So let's consider two of them. So for practical purposes, we can think of these agents as individuals. So we have a certain supply of resources. Which you may think of as, for instance, money. And that's represented by omega. Yep. And this is a number which is greater than or equal to 0. These resources must be allocated between these two agents. Okay, must be distributed. Okay, and each of them has a utility function. Okay, so this utility function will be a function which we are going to represent by u subindex I, which is going to go from r plus into r plus for I equal 1 to 2. Okay. So in other words, UI is going to be a function of some xi. And xi is going to be called the allocation. Okay, so the allocation money on agent I. Okay, for agent I. So what is the idea before I change the page? So there is this amount of resources. Certain amount is going to be allocated for agent 1 and certain amount is going to be allocated for agent 2. Okay. Those amounts are going to be represented by x1 and x2. So that's essentially the idea. And may I change the page?
Yes.
Yes, thank you. And the pair x1 comma x2 is going to be called the allocation vector. Okay, so we are going to say that an allocation is feasible if the following conditions are satisfied. The first one is that x1 and x2 are greater than or equal to 0, and that the sum of the allocations does not exceed the total amount of supplies to be allocated. And this provides us with the feasible region. Which is going to be this set that's going to depend on omega. Is the collection of all allocation vectors with the property that x1 plus x2 is less than or equal to omega. Okay. I'm going to give a definition here. So we're going to say that an allocation is Pareto optimal Pareto optimal. If actually there is no other allocation, okay, there exists no other allocation, let's say x1 prime, x2 prime, with the property that ui of xi prime is greater than or equal to ui of xi for I equal 1 to 2. And a strict inequality is happens in at least one of these two inequalities. Okay. Now, in some kind of problems, usually, in order to consider Pareto optimal problems, usually the function u will be a function that depends not only of x1 and x2, but also on certain parameter alpha. And the expression of this function is usually of the form alpha times u1 x1 plus 1 minus alpha u2 of x2. This new parameter is a number which is between 0 and 1. But in general, the problem is the following. So we would like to maximize the utility function, which may depend on this additional parameter also, and x1 comma x2 must be in the feasible region. Okay. Okay, so those are some problems in mathematical economics in which maximization or minimization are involved. I wanted to talk about two other problems, but I guess I have no much time. I'm going to let you read them and understand them as homework. So the next problem will be what we call optimal provision of public goods. Okay, so I'm going to leave this problem to you for you to study. So read it, please. Okay. And there is another one. May I change the page?
Yes.
Yes, okay. So please read also this next problem, which is optimal commodity taxation. Okay. Yeah, so try to read them during this weekend and try to understand all the previous problems. So maybe it helps sometimes to provide some concrete examples to make sense out of them. Let's say if we're talking about some company, maybe we can think about some specific company, let's say candy company or gasoline company or something like that. Okay. Before I let you go, I'd like to provide a remark. We know that we are going to study problems, so we will study optimization problems, optimization for functions that go from some set of Rn into R. So we know that. So all the problems that we're going to talk about related to optimization problems in this course will be related to this type of functions. Okay, so what do we want to know? What do we want to do? So in this course, what we are going to do is sometimes we would like to know if the optimization problem has solution. In the case that they have solution, the question is, are solutions unique? So we also would like to establish conditions for both existence and uniqueness of solutions. And we are also going to develop some mathematical theory to solve these questions. Okay. So about the roadmap of this course. So the first thing I would like to do is to consider the case of unconstrained optimization. So that's optimization problems, maximization, minimization without constraints. And we are going to study a theorem in order to determine if some problem has solution or not. So we are going to see what we call the Weierstrass theorem. So still in unconstrained optimization, so we are going to remember some results from calculus. especially criteria for the first and second derivative to determine if some critical point is actually a maximum or minimum. And then we are going to consider constraint optimization. So first, we're going to consider constraints in the form of identity constraints, equality constraints. And the most important tool in this case will be Lagrange's theorem. And then we're going to talk about inequality constraints. And the most important tool in this case will be the Kahn-Tucker theorem. So this is to start with, but then things are going to get more interesting, right? For instance, the question is, what happens if in some constraint problem you have both equality and inequality constraints? So there will be a version of the Kahn-Tucker theorem in that case. We're going to apply it. And then we're going to study a little bit about convex optimization. Okay, so this is what we are going to do. These are some problems. The problems that we mentioned today will be some problems that will appear eventually in some of the applications. Okay, but the most important things are still to come. Okay, so starting next week, I'm going to start to talk about unconstrained optimization and then constraint optimization. Ladies, do you have any questions?
No.
No? Everything was clear?
Sure. Yes.
Sure. Okay. So I'm going to stop sharing. Okay, so I have some homework. I already posted some homework, as you can see in the Moodle page. Please try to start to solve those problems. And if you have any questions, you will let me know, right?
Yes.
Yes.
Okay, very well. So any comment?
No.
No.
No. How is Hilary?
Still sick.
Still sick? Okay. Okay. Well, I hope she gets better. So say hi to her on my behalf. And you guys take good care and enjoy your weekend, please.
You
You
too.
too. Bye.
Goodbye.